Okay, good evening all. I'm starting recording for second problem solving session of the course, Mechanics of Materials. Right. So let's start with today's topic. Uh, Last week we have seen in week one we have seen the basics of mechanics of material, the basic concepts of mechanics of materials. First, we would have seen force and displacement. There are four basic tenets of mechanics of materials. The force, displacements. In mechanics of rigid bodies, we can relate force directly with displacements, whereas in mechanics of deformable bodies, we cannot relate force with displacement. So we have to find some other way through which we have to relate this force and displacement. So what we do, we convert force into stress and we convert displacements into strain, and this force and stress relation we call as equilibrium equation. And the relation between the displacement and the strain we call strain displacement relation, and the relation from strain to displacement we call compatibility condition. And the last link here, the displacement between stress and strain, we call as constitutive relation. So these are the basic tenets of mechanics of material, right? So this week we'll start looking at what each of them one by one. So in week two, Sir Professor Saravanan would have covered what is force, what is displacement, and also you would have started about stress, right? So after that, we'll see strain, then constitutive relation one by one, the remaining things. So in this week, number two problem solving session, we'll see problems from two things. Number one, majorly from displacements, displacement field and deformation field, and then from stresses, traction, the concept of traction and the stress vector. And also at the end, we'll see some animation which will help us to understand, visualize the problems that we are solving in assignments, right? We'll use computer tools to visualize the problems. So first, we'll start off with a force. So force, uh, indirectly, we can say, if someone asks, the question is, what is a force? What is a force? And is it a scalar or vector? So the basic question, if someone asks, we define force is a imaginary thing which we use to measure or represent displacements of the bodies, and we say force is a vector quantity because if it is a scalar, when we add and superpose, it would be same. But in case of force, this is not the same. So we say force is a vector quantity. This can also be proved using three spring balance as shown in the lecture. I'll take a problem from a displacement, the concept of displacement. Say, assume we have a body given like x, y, z. Is an element of where x is the element ranging from 0 to 1. Y is again ranging from 0 to 1, and Z is ranging from 0 to 1. And the deformation field is given for this problem. The deformation field is given by x is equal to capital X, y equal to capital Y plus a times z, and z is equal to z minus ay. Okay, so this is the question. Now, quickly, what do we mean by a body? Body, here we define body as a collection of ordered, countable or countless set. So here in this problem, we have been given with a countless set because 0 to 1 has a lot of points, real numbers. So we say here it's continuum, not discrete. If it is a countable, we say it's a discrete one. So that's a body. And there is something given here called deformation field. What do we mean by deformation field? First, let me draw a body. It can be any body of irregular shape, but in this problem, it is given such that x varies from 0 to 1, y varies from 0 to 1, and z varies from 0 to 1. So what we'll get here is we'll get a cube with side 1 unit. So this is say x-axis, this is y-axis, this is z-axis. So we will get x, y, z, 1, 1. We'll get a cube. I'm drawing, it should come out. So this is a body given in this problem. So what do we mean by the deformation field is for that we need to understand something called reference configuration and current configuration. Say suppose a body is here, some irregular body. After applying force, this body has been displaced to some other location. So with respect to the coordinate system x, y, and z. So this we say reference configuration. So the reference configuration is the initial state of the body, and the current configuration is the final state of the body. So this is reference configuration, and this is initial current configuration. Okay. Suppose there is a point A here initially, and the position vector of this point A with respect to this x, y, and z axis is say assume it is something called capital X, capital X vector, and the same point after deformation it will move on to somewhere here a dash. Again its position vector, assume it is given by small x, small x. So the relation between this capital X, the current configuration position vector, and sorry, the reference configuration position vector and the current configuration position vector, we call as the deformation field. So for example, here we can write, by the way, what do we mean by displacement? The displacement is nothing but the vector here. From here to here is the displacement, the shortest distance between those 2 points traveled. Now, using vector law of addition, we can write u capital X plus u vector is equal to small x vector. So, u vector can be written as small x minus capital X. Right? So, this is u vector. U vector is called displacement vector. Displacement vector. And the relation between this x, small x, and capital X, we call deformation field. If it is also a function of time, we call it a motion field. Say, I can write the small x vector as some function psi of capital X comma t. So this we call sorry, this is called motion field. The motion field, the function. motion field. And a point to note here, this should be a one-to-one function, because if it is not a one-to-one function, it means the particles are penetrating inside. This is a strict assumption in this course. We assume the motion field is always a one-on-one function. Okay, and suppose if I want to write in terms of small x and t, we can also write that we say psi inverse of small x comma t. Okay, this we say this is the material representation, and this we say is the spatial representation. Material representation we also call Lagrangian representation, and spatial representation we also call Eulerian representation. Okay, so this is the basics, what would have been covered in the lecture. Now, if I want to write the displacement field is nothing but that u vector. U vector is small x minus capital X. In terms of reference configuration or material representation, I can write psi of capital X comma t minus capital X, or we can, in terms of spatial representation, we can write small x minus psi inverse of small x comma t. Okay, so this is what we would have watched in the lecture. Now let's move back to the question we have. So we have given some deformation field. See here, small x equal to capital X. The deformation field given for us is, we were not given with motion field, we are given with deformation field. What do we mean by deformation field? If this t is not there, it's not a function of time, we call that as a deformation field. So deformation field here, what we have given with this, small x equal to capital X, small x equal to capital X, small y equal to capital Y plus az, small y equal to capital Y plus az, and small z equal to capital Z minus ay. Okay. So this is what given in the question. Now what they are asking in the question, number one, they are asking to find displacement vector components in material form and spatial form. I request, whenever as parallelly, it will be good if you are doing it along, so that we all will do along, so you also will be feeling interesting. You can find the answer. You can also tell me if I am making any mistake. So displacement vector components in material form and spatial form. We have to find. This is the first question. So let's solve this question. For this given deformation field, we need to find the displacement vector component in material form as well as spatial form. So u vector, we know displacement vector is given by small x minus capital X. So first let's try material form or Lagrangian form. So material form means it should be in reference configuration. So u vector is equal to, instead of small x, I can write capital X. By the way, here there would have been some confusion. This is representing a vector. Each of this representing a vector. A bar, one line under it, we say it's a vector. If I am not using that, we say it's a scalar. So a vector will have three components. Components along x-axis, component along y-axis, component along z-axis. So this x will have ex component, ey component, ez component. Also the capital X will have its own ex, ey, ez component. Okay. So here let's let's do. Yeah. So x is small x is capital X they have given minus capital X. This is EX component plus small y is capital Y plus AZ minus capital Y plus Z is capital Z minus AY minus capital Z. This is EY and this is EZ. If you are not getting anything, please feel free to unmute and stop me and ask at the same time. So this is 0 EX plus AZ EY plus, sorry, minus AZ, AY EZ. Okay. So this is 0. A times Z EY minus AY EZ. So this is the displacement vector components in material form. Along X, it is 0. Along Y, along Y, along I'll write along EX, along EY, it is AZ. Along EZ, it is minus AY. Okay, these are the components of the displacement vector. Next, let's move on to the spatial form. So spatial form. How to solve spatial form? Same, but instead of reference configuration, we are going to go with the current configuration, right? So u vector is equal to small x vector minus, so instead of capital X vector, we have to substitute small x. So here, since small x is equal to capital X, we can write this also capital X. This is Ex component plus y small y minus capital Y. So capital Y here, it's not given straightforward. So we have to do algebra in order to find capital Y and capital Y and capital Z in terms of small y and small z and small x. So we just have to simplify equations. So let's do that. So y equal to capital Y plus a z is given. So let's do substitution method. So and small z equal to where is it? Capital Z minus AY, right? This is capital Y, sorry. This is capital Y. This is again capital Z. I think I should write more clearly the capital and small. Sorry for the mistake. Yeah, so we need what is y in terms of function of small y. So similarly z in terms of small z. Small z or small x, y and z, and here also x, y and z. So just do substitution method and let's find it out. So capital Y can be substituted as small y minus a z, and let's substitute it back. So z is equal to capital Z minus a into small y minus ay, right? So I assume this is number one, equation number one, equation number two, and from one I am writing this equation number three, and equation three in two implies z is equal to this z A into Y, this is Z. AY plus A square Z.
Sir, in equation 3, why it is minus AZ?
1 second. Yeah, I'm substituting in terms of from 1 plus AZ, like I'm subtracting minus AZ on both sides from equation number 1. So, is that right?
Yes, sir. Uh, Small y equal capital Y plus AZ, that is equation 1. So it is replaced by
Yeah.
small y
Huh.
minus AZ.
Yeah, yeah.
Okay.
So we want to find capital X, Y, Z, small y, X, capital X, Y, Z in terms of small x, small y, small z. So we are just doing substitution here. Okay. Is that, can I proceed?
Yes, sir.
Oh, thank you. Right. So where we are, I have substituted equation number 3, which is capital Y equal to Y minus AZ in equation number 2. So this becomes Z is equal to capital, little uh, differentiate capital Z minus A into Y minus this is also capital Z. So AZ. Now small z equal to Z 1 plus A square minus AY. So Z plus AY by 1 plus A square equal to Z. Done. So we have found capital Z in terms of small z and small y. Now let's substitute it, let it be equation number 4 and substitute it back to get capital Y. 4 in 3 implies capital Y is equal to small y minus A times small z plus A into Y divided by 1 plus A square. So this is equal to Y plus A square Y minus AZ minus A square Y by 1 plus A square. So this is equal to A square Y minus A square Y cancel. So Y minus AZ by 1 plus A square. So this is capital Y done. Now let's substitute these 4 and 5 in the original displacement vector. So where we are here, I'll shift it here. So we are here. So y minus capital Y. So capital Y is y minus az by 1 plus a square ey plus z minus capital Z. Capital Z is z plus a y by 1 plus a square. Okay, this is easy. That's it. So we can do again substitution and simplify this vector further. Okay, so this is the displacement vector in spatial representation or Eulerian representation. Fine. So this is the first part of the question. Next, let's move on to the second part of the question. The location of particle originally at simple 1 comma 0 comma 1. So you can find out the location of particle originally at 1 comma 0 comma 1. What they are asking? So originally at 1 comma 0 comma 1 means at reference configuration. So they have given capital X, capital Y, capital Z, or small x, small y, small z. Which one they have given in the question? This is the only thing we have to know. So originally means reference configuration. Reference means capital X, capital Y, capital Z. So this is equal to 1 comma 0 comma 1. And we have to find the location of where this particle at 1 comma 0 comma 1 went after the deformation, right? So we already have this relation. We want small x is equal to what? So what is small x? Is equal to capital X. So capital X is 1 here, right? And what is small y in terms of capital X, capital Y, capital Z? Small y is capital Y plus AZ. Capital Y plus AZ. So capital Y is 0 plus A times Z is 1. So A. Okay. Small z is, what is small z in terms of capital Z? Capital Z minus AY. Capital Z minus AY. So this is equal to 1 minus 0, which is 1. So that point 1 comma 0 comma 1 for the given deformation field, it has moved to 1 comma a comma 1. Okay. And question number C, subdivision C, location of particle uh, in the reference configuration if its current position is 0.5 comma 0.5 comma 0.4. Can you try? So location of particle in the reference configuration if its current position is 0.5 comma 0.5 comma 0.4. So here they are asking capital X, capital Y, capital Z equal to what? Given small x, small y, small z has 0.5 comma 0.5 comma 0.4. This is what given, right? So capital X equal to, we just found capital X equal to small x. So small x is 0.5 and oh, capital Y equal to, where is capital Y? Y minus AZ by 1 plus A square. Y minus AZ by 1 plus A square, which is 0.5 minus 0.5A by 1 plus A square. We can take 0.5 as common. So 1 minus A by 1 plus A square. Okay. And capital Z is Z plus AY by 1 plus A square. Z plus AY by 1 plus A square, which is zero point 0.4 plus 0.5 y by 1 plus A square. Done? So that's it. And fourth subdivision number D is displacement of particle originally at 1 comma 0 comma 1. So at 1 comma 0 comma 1, what is the displacement of the particle? So here they are asking the displacement. They have given the reference configuration, that is x comma y comma z. Capital X comma capital Y comma capital Z is 1 comma 0 comma 1. And they are asking you, we have already found the u in terms of material representation. That is AZ EY minus AY EZ. AZE, or it again should be capital. AZEY minus AYEZ. Right? This is what we have found. Let's substitute the XYZ here. So A times EY minus 0, right? So that's it. Final question. You would have found out what would be the final question. Displacement of particle currently at 0.5 comma 0.5 comma 0.4. Again, we already know the displacement u is equal to capital X minus small x, capital X minus, sorry, small x minus 0. So 0, 0 ex plus for y minus, okay, this we have to simplify, right? Let me simplify it here so that it's easy. 0 ex plus 1 plus a square, y plus a square, y minus y will get cancelled. So a square y plus az by 1 plus a square uy. Here similarly z minus z will get cancelled and a square z minus ay by 1 plus a square easy, right? So this is u. Now we have to, they have given y and z as 0.5 and 0.4. So let's do it. Oh, I have to remember 0.5 a square plus 0.4 a divided by 1 plus a square ey plus, what is the easy component? A square z minus ay. A square, this is 0.4 a square minus 0.5 a by 1 plus a square, right? Yeah, 1 plus a square. Easy, that's it. Okay, just simple substitution once if you found the vector. So that's it. Right, so this finish the first problem. So this is a sample problem. Here we can understand what do we mean by uh, deformation field. What do we mean by a reference configuration? What do we mean by a current configuration? What is a displacement vector? What is a motion field? What is a displacement field? What is a deformation field? And how do we represent in terms of material representation? How do we represent in terms of spatial representation? All these concepts are covered in this problem. Okay, so this is actually the first topic. Let's move on to one more problem similar to the assignment problem that you have. Okay. Problem number 2 for the day. Given small x is equal to capital X plus zero point 0.4 y. This is the deformation field. Y equal to 1.3 y and z equal to capital Z. Okay, this is the deformation field given. Okay, now what we have to find? The component of displacement undergone by a material particle that occupied point 0.1 comma point 0.1 comma point 0.1 in reference configuration is dash. So we need to find the component of displacement undergone by a material particle that occupied point 0.1 comma point 0.1 comma point 0.1 in reference configuration. So let's solve it. So given capital X comma capital Y comma capital Z is 0.1 comma 0.1 comma 0.1. So first we need to find the displacement vector, that is u vector. So displacement vector is what? Small x minus capital X. So they have given small x in terms of capital X, capital Y, capital Z. So directly we can substitute it here. So capital X plus zero point 0.4 capital Y minus capital X. So this is equal to 0.4y. Capital this and this cancel. Okay, this is the x component. Okay, let me write in terms of vector, that is more compact and good. So, okay, x, y, z. Usually, this is the vector representation that we follow in this course. So, let me write in terms of column vector. And y is 1.3y. Small y is 1.3y minus capital Y, which is 0.3y. And z is capital Z minus again capital Z, 0. Okay, that's it. So this is actually 0.4y ex plus 0.3y ey plus 0 ez. Okay, this is the displacement vector. Now we have to substitute this 0.1 comma 0.1 comma 0.1. Add zero point 0.1 comma 0.1 comma 0.1. U vector will be equal to 0.04 ex plus 0.03 ey. That's it. Okay, I just multiplied the value of capital Y in this equation. Okay. So the x component of the displacement field is what? So x component of displacement field, they are asking three subdivisions. X component of displacement field is, that's ux is 0.04, and y component uy is 0.03, z component is 0. Okay, done. So this is a problem. And problem number 3, I hope again no questions. If there are any questions, please feel free to ask me. Moving on to the next question, same deformation field, but a change is we have to find problem number 3, same deformation field as above. But what we have to find is component of displacement undergone by a material particle that is currently occupying. This is the keyword. Currently occupying point 0.1 comma point 0.1 comma point is dash. Same. Okay. So how will we find same deformation field? Let me copy this. Okay, it's the same deformation field. So we need to find the component of displacement that is currently occupying. We can write cap again. We have to use the algebra, basic algebra, in order to replace this in terms of capital Y. So let's take this as equation number 1, equation number 2, equation number 3. So equation number 3 is direct. Capital Z is small z. Okay. Equation number 2 is also direct. Capital Y is equal to small y by 1.3. Equation number 1, we have to substitute. Equation number the same. 4. In substitute 4 in 1 implies small x equal to capital X plus zero point 0.4 times y by 1.3. So I want capital X. So I'm going to do it at that side. So 4 by 13 y. Okay, that's it. Equation number 5. Okay, we have everything now. Let's solve the problem. U is equal to u vector equal to small x vector minus capital X vector. So this time we are going to substitute capital X in terms of small x. So this is x minus capital X is what? Small x plus 4 by 13 y. Okay. And small y is small y. Capital Y is y divided by 1.3. And this is the vector, column vector. And z is what? Small z minus capital Z is z. So this is 0. Okay. So x minus x will become 0. So 4 by 13 y, 1.3 minus 1 is 0.3, 3 by 13 y and 0. That's it. So u vector is, this means 4 by 13 y ex plus 3 by 13 y ey plus 0 ez. Okay. Now they have given zero point 0.1 comma zero point 0.1 comma zero point 0.1. This is small x comma small y comma small z currently. So 0 point 0.1 we have to substitute. So this is equal to 0.4 by 13. Let me write add, therefore add 0 0.1 comma 0 0.1 comma 0 0.1. U vector will be 4 by 13, no, 0 0.4 by 13 ex plus 0 0.3 by 13 ey. This is u vector, that's it. Okay. Right. So this is one variety of problem we have seen where they have given us the deformation field and they are asking us the displacement field. So this is problem category number 1 under displacement. And let's move on to the another category, the last category of problems in displacement. That is, they have given us the displacement field and they are asking us the deformation field back. So this, let's move on to the second category. From displacement field to deformation field. Okay, let's take a problem right away. A easy one. This is problem number 4. So ux is equal to 0.05 capital Y. Uy is equal to minus 0.09 capital X. Uz equal to minus 0.01 capital Z. Okay. So they have given the displacement component, that is the u vector is 0.05 y ex minus 0.09 x ey minus 0.01. This is given. Easy. Okay. Now they are asking the component of component displacement undergone by a material particle that occupied the point 1 comma 1 comma 1 in reference configuration. So this is a question. So they have given us the displacement field and we need to find the components of displacement undergone by a material particle that is currently occupying the point 0.5 comma 1 comma 1 comma 1. So let's solve. U vector equal to small x vector minus capital X vector. So x comma y comma z is directly given. So we can write, so x comma y comma z is 1 comma 1 comma 1. So this implies u vector equal to, okay, for this we need the small x smaller the deformation field, right? This is equal to small x minus capital X is equal to what? I'm writing one by one, and small y minus capital Y. Let's write in a new page. Small x minus capital X, small y minus capital Y, small z minus capital Z. This is u vector, right? This is equal to what is they have given? 0.05 minus 0.09 minus 0.01 capitals. Okay, so this implies small x is equal to capital X plus 0. We got the deformation field. That's it. So y equal to capital Y minus 0.09 capital Y. Right? And small z equal to z minus 0.01 capital Z. Okay, that's it. Now capital X, capital Y, capital Z is given as 1 comma 1 comma 1. So let's substitute back it here. Add 1 comma 1 comma 1. X is equal to 1 plus 0.05. 1.05 and y is equal to 1 minus 0.09.
Sir, the given y is uy minus 0.09 x capital X or capital Y, sir, in given problem. That is the x.
Ux
Uy.
uy is minus 0.09 capital
Uh,
X.
yes, sir. When we are coming to substitution, that is the x, right, sir?
Where? Okay. X, right?
Here
Sorry.
in my
Yeah, yeah, correct. Here, right?
yes, sir, yes, sir.
Thank you. Yeah.
Okay.
Yeah, correct. Fine. Yeah, since it's 1 comma 1 comma 1, finally saved in the answer 0.91. And small c is equal to 1 minus 0.01 is 0.99. Fine. That's it. Okay. Is there any questions from this? Is this fine?
Yes, sir.
Thank you. Now, again, we can solve one more problem, the final problem from the concept of displacement for today. Problem number 5. X is equal to last problem. So ux is given as zero point 0.5 capital X plus zero point 0.1 capital Y. Uy is given as 0.05 capital Y, and uz is given as zero point 0.1 capital Z. Right? So we need to find same question. I have just changed the displacement field, same point, but this time let's solve 1 comma 1 comma 1 in current configuration. Current configuration. So we need to find what is the position of a particle at 1 comma 1 comma 1 in the current this particle 1 comma 1 comma 1 is current configuration. This small x, small y, small z. We need to find what is capital X, capital Y, capital Z in the reference configuration. Okay. So last problem it was the other way around. Now it is the vice versa case. So let's solve it as before. So ux, uy, uz is given. So u vector is again small x vector minus capital X vector. So small x vector this is given as x minus capital X, y minus capital Y, z minus capital Z is equal to 0.5 capital X plus 0.1 capital Y, 0.05 capital Y, 0.1 capital Z. Okay. So this is equal to, let's take these equations one by one. So please let's solve. Small z minus capital Z equal to zero point 0.1 capital Z. So we need capital X, capital Y, capital Z in terms of small x, small y, small z. So Z is common. 1 plus zero point 0.1 is 1.1. So capital Z is equal to small z divided by 1.1. 1 done. Second one, y minus capital Y is equal to 0.05 capital Y. So y equal to 1.05 capital Y. So capital Y equal to small y by 1.05. Done. The last one. Small x minus capital X is equal to 0.5 x plus zero point 0.1 y. Okay. So x minus capital X is equal to, let's substitute capital Y, zero point 0.1 times y by 1.05. So we need x, capital X. So I am going to take x on one side. So 1.5x capital X is equal to x small x minus 110 by 105 small y. So capital X is equal to uh, capital X is equal to x by 1.5 minus 100 by 15 into 105. So when we substitute the points 1 comma 1 comma 1, so we'll get add 1 comma 1 comma 1, we'll get capital X as 1 by 1.5 minus 100 by 15 times 105. So this we'll get, and capital Y as 1 by 1.05, and small z as 1 by 1.1. I hope you're also getting the same answer. So with this, you can solve and you can compute. Fine. So this completes the displacement concept. So out of these four, its force is done, displacement is done. Now the third concept is stress. Okay, so let's move on to some problems from the concept of stress. If there are any questions in the displacement field, you can ask. At the end, we'll see some animation which is showing the current and reference configuration. Any questions from displacement field so far? I hope if you have any, please feel free to ask. Okay. If no questions, let's move on. So stress. Okay. So I'll quickly summarize or the things which we would have covered in week two related to stress. So to understand stress, we need to know something called traction. Traction. Actually, this word uh, in my UG, stress is nothing but force by area. This is what I have studied, but actually, it has something to do with traction in terms of deeper understanding. So, traction. What do you mean by a traction? Like, suppose if we have a body, if we cut, there can be some forces acting on this body. It can be any, this body would have been resting on some support, doesn't matter. Okay, we can draw the free body of this body by removing the support. So there will be some forces. This body currently is in equilibrium. Now, when we cut this body along some section, we are exposed to its internal forces. Assume these two are same, so same forces are there. One, two, three, and let me remove this reaction, the support, and replace it with some reactions. Okay, some unknown reactions and loads. So now by traction, we mean the distributed force along a cut surface. The distribution force along a cut surface. See, at this cut surface, there will be some distribution force. Some force are distributed over this cut surface. According to Newton's law, this should be equal and opposite. This distributed force we call as the traction. Okay, uh, right? This traction is a function of three things. Number one, we can easily relate or understand. Number one, that is, it is a function of position vector. At every point, the traction will be different, right? So traction is a function of position vector. So traction, we say t of n is a vector. T. Let me represent it with a vector. What color? Yeah, this one. Some t of n. where n is the normal of this plane. Okay, this n normal, outward normal of that plane. Okay, traction vector along n. So t of n. So see here, there are two under bars. One is under t, one is under n. Because traction is also a vector, the normal is also a vector. So t of n is a function of position vector x, comma, time, time. Yeah, traction vector would change with respect to time. And also, it's a function of the normal. So there are three things it depends on: the position vector, the time, and the normal, right? So this is a traction vector. Okay. And there is an important property of this traction which comes from Newton's third law, that is T's of n plus T's of n star. N star is, assume this is T's of n, the opposite thing, the one which is coming from the opposite. This is T's of n star. So this is equal to 0. Okay. Because of Newton's third law. Both will be equal and opposite. This is a property that we need to understand, remember. Okay. Here instead of capital X, let me write small x, the current one for synchronization with the lectures. Okay, fine. Now, let's move on to the stress. So, what do we mean by stress? So, we have two vectors here. Number one is a traction vector. Number two is a normal vector. So at every point in a plane, in every point we have a normal vector, and there will be some traction vector. So we need some quantity that maps the normal vector to a traction vector. That quantity, that function, we say it's a function, a linear function. We should see what is a linear function, but as of now, the linear function which maps the normal vector with the traction vector we call as stress vector. So T's of n is equal to sigma. It's a second order tensor. I'm putting two underscore here, which means a second order tensor, right? A tensor, and n cap. So this we say Cauchy theorem. Okay, this is how we find traction. Sigma is the stress tensor. So we'll see the problems, which will actually tells us what is the sigma. We can represent in terms of a 3 by 3 matrix, a tensor, and we have 9 components of sigma. Each of them has a physical meaning. Like a vector has 3 components. A vector is a first order tensor. Scalar is a zeroth order tensor. This is the second order tensor, right? So this has 9 components in it. And linear function, here we mean f of, it should obey two laws, the superposition and scaling. F of alpha times x1 plus beta times x2 is equal to alpha times f of x1 plus beta times f of x2, where alpha and beta are constant, and x1, x2, and alpha times x1 plus beta times x2 are in the domain of the function. Now, these are the condition. Are in domain of the function. Okay. So here a small point to note. So this linearity, in lower classes we would have studied y equal to mx plus c is a linear curve, but when we substitute it here, you would have seen in the lecture it is not linear. So linear here, the definition we obey or we assume it follows these two principles, the scaling and superposition. Y equal to mx is a linear. And similarly, we can represent a differential equation as a linear function. Okay, so here the stress tensor should be a linear function. Fine. Now, quickly, let me just revise the tensor algebra. Tensor algebra. You don't have problems exclusively from tensor algebra, but still, in order to understand the tensor, we need to be clear with this tensor algebra concept. So, what do we mean by a tensor? What do we mean by tensor? Say, suppose if we have a vector y, x in this Cartesian coordinate system, some x, ex, ey, and ez. So as we saw before, we have two vectors. Vector number one, which is x, vector number two, which is y. So we need to find y given for a given x. I know x. What is y? So how it will we will find is through the second order tensor, a linear function which maps one vector into another vector is called a second order tensor, right? So this is equal to some let me say a double. So this is a tensor definition, a linear mapping between two directed line segments or two vectors. A vector is a directed line segment, right? Now, how will we represent this tensor using this initial notation? Because this A vector, sorry, A tensor is equal to Aij Ei tensor product Ej. Okay, here we need to understand what do we mean by tensor product. These are all some basic definitions that we fix so that we will use those definitions later to solve the problems physically. So tensor product, we would have seen vector product, scalar product. This is tensor product. So as per definition, tensor product means, say, suppose if we have two vectors, a tensor product b C acted on C is equal to B C times A. This is the definition that we are assuming. Okay. Here, suppose this A is A cross A tensor product B, and this is C. This will be given by some X. Okay, because B dot C will give us a scalar. A dot product of two vectors is a scalar, and a scalar times a vector is going to give us the vector, right? So RHS is a vector. LHS, a tensor product of A and B is a tensor. That's A double underscore. C is a vector. So AC equal to X. So this is, we say, the tensor product between A and B. Okay. This A is the second order tensor. So now when we expand this using initial notation, I and j are the dummy index. So we have to sum it from 1 to 3. So this is equal to A11 E1 tensor product E2 plus A12 E1 tensor product E2 plus A13 E1 tensor product E3 plus A21 E1 tensor product E2 tensor product E1 A22 E2 tensor product E2 plus A23 E2 tensor product E3 plus all this A31, E3 tensor product E1, A32, E3 tensor product E2 plus A33, E3 tensor product E3. So what is E1 tensor product E2? If E1 is EX, EY, or E1, E2, E3, both are same. They are orthonormal basis vector. So here, this A11, A12, A13 are the components of the second order tensor. We have 9 components, and this E1 tensor product E2 is one of the bases. E1, why here? Sorry, it should be E1 tensor product E1, right? Okay, so this is one basis, this is one basis, this is one basis, and there are 9 bases. Like a vector has 3 components and 3 bases, the EX, EY, EZ. The tensor, second order tensor has 9 components and 9 bases. Now, if you want to find the components, how will we find the components of the tensor? Finding components of the tensor. Say, suppose we have y equal to ax. Now let's write this in terms of initial notation. So this is equal to, in terms of initial notation, we write x vector is, how will we write x vector? Some x, say let's take xj, ej, okay? Because j is a dummy index again, so x1 e1 plus x2 e2 plus x3 e3. So shortly we can write xj ej. Right now, I can write yiei, right? Yiei is equal to a times xj ej. Okay, so yi, oh, let me write it here. Y vector equal to, so yi. Suppose if I want yi, what, how will we write? What is the ith component of y? So y vector dotted with ei, right? Right? The projection of y vector along ei axis. That's a definition of dot product. So substitute it back. So this is equal to a vector. So instead of y, I am substituting a. Let me write in different color. So instead of y, so a x dotted with ei. Okay. So again, x vector we can write, this is equal to a is as it is. Instead of x, we can write, since I have already used this I, so that's why, yeah, ej, xj, ej dotted with ei. Okay. So there is a definition of transpose. So this is equal to x j ai. Since x is a scalar, we can just put it in the front, ej dotted with ei. So this is equal to xj. This is aij. So actually, why we are doing this? We want to find the components of the tensor. The component of the tensor is aij, right? So aij is nothing but a tensor of ej dotted with ei. Okay, so that's it. So aij is a ej dotted with EI. Okay. So this is a component of a tensor. Now, if I want to represent this A tensor, so A, EJ dotted with EI, this is the component, and the basis is EI tensor product EJ. Okay. What is this A tensor product B? A vector is AI EI. B vector is BJ EJ. So using the definition, A tensor product B, no, let's write the components of A tensor product B of IJ. Ijth component of A tensor product B will be equal to A tensor product B times, just now we have seen ij component of A will be A tensor times EJ dotted with EI. Similarly, ij component of A cross A tensor product B will be A tensor product B times EJ dotted with EI. Right? So this is equal to A times B dotted with EJ time EI. This comes from this definition of tensor product. Okay. So this is equal to, again we can write A dot EI, a scalar, right? B dot EJ. Scalar is commutative, so you can simply rewrite like this. This is AI BJ. Okay, AI BJ. Fine, which means, say suppose I have E1 tensor product E1 is what E1 tensor product E1 is dot product of this 0 0 0. This is 1 0 0. So this will give us a 9 by 1, right? This is 3 by 1. This is 1 by 3. So this will give us 3 by 3. Okay. So A vector, similarly E1 tensor product E2 is 1 0 0 and 0 1 0. This will give us 0 1 0 0 0 0 0 0 0. Similarly, if I want to write E3 tensor product E3, it means 1, no, 0 0 1 times 0 0 1. 0 0 0 0 0 0 0 0 1. So these are all basis vectors, right? So there are 9 components, so 9 basis vector we'll get. Fine. So this is what it is. Now stress component, we have already seen the stress is nothing but a second order tensor that relates a traction vector, a normal vector with a traction vector. Let's continue there. Let's use all these mathematical concept of tensor in the stress, apply in the stress. But before that, we just need to know the definition of transpose. Transpose definition is, say suppose A B is equal to just A transpose tensor A dotted with B. Okay, this is the definition of transpose. Mathematical definition of transpose of a second order tensor. Okay, so now our aim is, what is the stress components of a stress tensor? Stress components of a stress. That's why we are doing all these. So stress components is what? Of a stress tensor, second order stress tensor, equal to what? Right? That is sigma ij is what? So sigma ij is, how can we write this is equal to, based on whatever we have seen, aij can be written as tensor times ej dotted with ei. So sigma of ej dotted with ei. Right? So now this is nothing but, I can, using the transpose definition, I can write this as sigma transpose ei dotted with ej. Okay. So what is sigma transpose? Sigma transpose of into ei. This is nothing but t's of ei, right? T's of ei dotted with ej. Okay, so sigma ij represent means what? A traction vector acting in acting along ei plane, acting not along, acting in ei plane, along which direction? Along ej direction. Okay, this is the meaning of sigma ij. Fine. Okay, suppose if I am asking, let's fix xyz. So if I am asking sigma xx, what is the meaning of sigma xx? Traction. So let's draw a body. Let's say this body has a coordinate system x, y, and z. Now, if I want to know the stress at the point, small some point P, what we will do? We will draw a cube, an infinitesimal cube, small cube. So, what is sigma xx? Traction vector acting in EX plane. What is EX plane? EX plane is a plane where the x is, the normal is along the x-axis. This is the EX plane. EX plane. So at this plane, in the x direction itself, there is some traction vector. T's of EX along EX. So this is sigma xx. Okay, sigma xx. Similarly, sigma xy means same. Let me copy this cube alone. The normal is same, but the direction, the yellow color is different. Right? The yellow color is acting upwards in the y direction. The plane is same. Green is same. This is EX plane only, but the direction is acting along y. So this traction is called sigma xy. T's of EX acting along y direction. This is sigma xy. Okay. Similarly, we can write sigma xz and so on. So let's draw it fully. A big cube. So this is x, sigma xx. Similarly, the back side, this is the side, right side of the cube. Similarly, left side pointing outwards is sigma xx, right? Why? Because left side, the outward normal, the positive outward normal is along the negative x-axis. So that is positive. Similarly, what will be this? Let's use different color. So what will be this? This plane is y plane, and the traction vector is acting along the y direction, right? So this is sigma yy. Similarly, this also sigma yy. Okay. And how about this, which is coming out of this screen? This is sigma zz. Similarly, going inside the screen, sigma zz. Okay, these three are normal traction. Similarly, there are six shear traction as well, which will be acting along the plane. So here, this is sigma x y. This will be sigma x y. Okay, here it's upward, here is downward. Okay, the negative x plane in the negative y direction. Okay, only then equilibrium will be satisfied. Newton's third law is followed. Fine. Similarly, in the x plane, we have one more shear component, that is sigma xz. Okay, this is sigma x in the z direction. This is sigma xz. Similarly, let's go with the y plane. Here, this is a y plane. So here, this is sigma y x, and similarly sigma yz. Okay, downward also sigma yx, sigma yz. Okay, similarly in the front face and the back face, we will have two more shear components. It's a little difficult for me to draw, it will get confused, but that is sigma z along x and z along y, right? So the front face is the positive z. So front positive z means, so this will be sigma zx. This is actually in the outward surface, and this would be sigma zy. Similarly, backside also we will have the same, but in the opposite direction. Okay, I am not drawing. Ashwamedh is backside. So these are the stress components, the meaning of the stress components. So here, the important point to note, to solve the assignment problem is T of n is equal to sigma transpose times n if you want to find the traction vector. And what is a tensor, a stress tensor? It's a linear function that maps a normal vector with the traction vector. So there are 9 components of sigma which is acting along each of the plane, right? So this is a second order tensor. The vector easily we can represent using just 3 components, but this tensor we need 9 components to represent. Okay, so stress is a physical quantity, but mathematically it is obeying the laws of a second order tensor. Okay, second order tensor has its own laws. Like in a vector, we will say the magnitude will remain the same even if we change the basis vectors. Like last week would have seen, if we change the x y z, we can play with the x y z, but still the vector is the vector. Okay, the ex ey ez change to ex star ey star ez star, the magnitude will not change in a vector, right? Here in a tensor, there are certain things which won't change. They are called invariants. Invariants. So invariance is something which will never change. Like if I want to tell 1 0 0 0 0 0 0 0. This is what this is representing a uniaxial state of stress, right? A bar subjected to along some force in a single direction, x direction alone, right? Suppose if I use the same thing, right? This is also a stress tensor, but this is also a uniaxial, the same state of stress, but the basis vector change. This you will understand in the upcoming week lecture series. You can watch the lectures. It's very interesting. Like, but our mind will say these both are same state of stress. Not this, not same state of stress. This is a uniaxial state of stress. This is something like xx, yy, everything is there. So how can it be uniaxial? But it's a tensor. When we compute the invariance of it, it will be the same. So what is these invariants? We'll see in the next upcoming week's course. There are three invariants. The trace of a tensor is the first invariant, and we have second and third formulas, right? So we can calculate that won't change if we change the basis x, y, z. If we change, it won't change. For a vector, the direction, the magnitude won't change if you change the basis. Similarly, for a tensor, these invariants won't change if you change the basis. Okay, so this is basic concepts. Quickly, let's dive into the problems. So we have been given with, this is problem number 6. So we have been given with some state of this, very easy solving problems. Problem number 6, given some state of stress. Say this is a plain state of stress. Plain state of stress means yz is 0. Yz is 0 in z part. Only xy is plane is there. So here this is 7. This is 7. And this is 5. This is also 5. Okay. So we need to find also, this is 3. This is 3. Okay. We need to we need to find what is sigma xx, what is sigma yy. Sigma xx, sigma xy, sigma xz, sigma yx, sigma yz, sigma y. No, let's go with order. Sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Okay. So for first, what is sigma xx in this problem? Sigma xx means in the x plane, let me give the basis vectors. So basis vector, this is x, this is y, ex, ey. Okay. So what is x means? Sigma xx means x plane along x direction. So this is my x plane, and this is my x direction. This is phi. Okay. And what is sigma xy means? X plane along y direction. This is 3. And what is sigma xz here? There's no xz. It's a plane state of stress. Plane state of stress. So plane state of stress, sigma x is 0. What is sigma yx? Sigma y, x is 3. By the way, this will be same because of moment equilibrium that you will see in the upcoming lectures. Sigma xy and sigma yx will be always same, and sigma zx will be always equal to xz because of the moment equilibrium that you will see. So that stress matrix will be always symmetric. Okay. If it is not symmetric, then there's some problem. So this is 7. Yy means along y plane in the y direction. Okay. Is there any mistake? Mm, Yx is okay. For this particular thing, I should have given here Yx is okay. This is going like this. This is going like this. Okay, I missed this here. Okay, yeah. Yz is 0. Zx is again 0. Zy is 0. Zz is 0. So these are the 9 components. Okay. Suppose in the question, mm, this is subdivision A. Let's subdivision B. They are giving something like this. Same, but I am going to change the direction of the signs. So this instead of going outward, this time it's coming inward, and this is going outward only. And shear like this, and these two form a clockwise moment. So to overcome it, we need an anti-clockwise moment, right? Otherwise, it won't be in equilibrium. So this clockwise, so anti-clockwise. Anti-clockwise, how will we get like this, correct? Only these will form an anti-clockwise moment, right? Last problem, I missed that. So this is, say, this values are, say, this is 5, this is 5, this is 8, this is 8, this is 3. Shear is 3. Now let's represent in the matrix. Okay, sigma second order tensor is equal to, what is sigma xx? Sigma xx is along x plane in the x direction. So here it's 5. And what is sigma xy? Sigma xy means x plane in the y direction. 3. Is it right? No, because y direction, xy, here it's pointing downwards, but my y direction is upward, right? So this is my y, ex ey direction. So it is minus 3. Okay, and this is 0. Xz is 0, and zx is same, minus 3. In the negative x direction, it should have pointed negative y direction, that is positive. Okay, this is a sign convention that we follow, but here it's not doing the same, so it's negative. And here it's 8. Here also, what is sigma yy? Sigma yy means on the y plane, it should be in the y positive y direction, whereas in this problem it's pointing in the negative y direction, so it is negative 0, right? 0 0 0. Okay, usually in the plane state of stress, all these it will become a 2 by 2 matrix instead of a 3 by 3 matrix. Okay, that's it. Fine. Suppose if you don't have shear, if you have a biaxial state of stress, problem number subdivision 3. Suppose if we have something like this, question something like this. Okay, so this sigma will be, say this is 5 5, this is 8 8. So sigma will be, sigma xx is minus 5 compression. It's in the positive x plane, but my force is coming in the negative x direction, so we say minus 5. In sigma xy, there's no shear. of course plane, so we can simply put zeros in these regions. Sigma yx is again 0, sigma yy is -8 because y direction, and my force is pointing in the negative y. Okay, positive y plane, negative y direction, right? So that's it. So this is the stress tensor or the stress components. Fine. Suppose let's finish up with the final subdivision of the day, topic of the day, components of tensor, components of traction vector. Okay, suppose they are asking, they have given us the plane, the normal, say t is say n cap is equal to 1 by root 2 ex plus ey. Okay, and they have given some stress tensor. Let's take this tensor itself. The tensor sigma is equal to 5 minus 3 -3 8 0 0 0 0 0. Okay, this is the stress sensor, and they are asking what is the traction along n equal to what? Okay, on this plane, what is the traction they are asking? How will we find? We know traction along a vector along n will be sigma transpose n cap, right? So this is equal to, the sigma transpose is coming from the transpose definition that we would have seen, ij e I dot ej. So sigma transpose is same, sigma equal to sigma transpose. So 0 0 minus 3 8 0 0 0 0 along 1 by 2 1 by root 2 1 by root 2 0. This is equal to 5 by root 2 minus 3 by root 2. This is 3 by 3 matrix, 3 by 1 vector. So we will get a 3 by 1 vector. Okay, minus 3 by root 2 plus 8 by root 2. This is 0. Fine. So this is traction. That is 5 by root 2. 5 minus 3 is 2. 2 by root 2 is 2 by root 2 is root 2. Okay, root 2 ex. Similarly, 8 minus 3 is 5. 5 by root 2 ey plus 0 ez. This is traction vector. Okay. So given a force, we can find the distributed force at any cut surface. Fine. That's it. Okay. So this actually completes it. Let's finally see animation which is showing a simple shear deformation. Say suppose, okay, I hope there are no questions. If there are any question, you can ask me from whatever we have seen. I have completed all the topics and the problems of the topics. So finally, we'll see some animations to understand this displacement field. Say suppose I have x equal to capital X plus ay and small y equal to capital Y. Okay. Say this is x, body is from x to 4 and this is from y 0 to 4. X is from 0 to 4, y to from 0 to 4. Okay. So let me stop the screen and share the other screen. See, here I have simple shear deformation. I hope my screen is visible.
No, sir.
Oh, it's not visible.
Now visible, sir. Visible.
Thank you. So here, let's take small x is equal to x plus ay. So I am giving small x is x plus ay, and small y is capital Y, as per I have given in the question. Okay. So this is the initial reference configuration. Okay. This A here represent the time. Okay, it's this t equal to 0, t equal to 1, t equal to 2. As time changes, it changes. Fine. So we saw the motion field and deformation field, right? We have seen in the example, we have seen something called x equal to a plus y something. So that actually represent the time component. So here assume a is some constant. So this is the initial, yeah, initial configuration, the reference configuration. The time is 0. The final configuration, the time would have been 1 second, 2 seconds, something. Let's stop it as 1 second. So a equal to 1. So for this, my vector. So I can draw a displacement vector. Second. Okay, here I can't draw. I hope I can draw, but you can assume, say, suppose at 2 comma 0, at this point that I'm showing the cursor here, 2 comma 0, there's a particle. Okay, I have already given you the displacement field, sorry, deformation field, small x equal to capital X plus ay, small y equal to capital Y. We can solve that and we can substitute. If we substitute x equal to 2 comma 0, if what will be small x 2 plus 0y, right? Because capital Y is 0. So which is 2. See, for this particular deformation field, at x equals 0, it's not moving anywhere. It's as it is, simply standing there, right? And suppose if I take a point here, 1 comma 1, capital X is 1, small y is 1. So you just substitute there in the deformation field. Small x will be equal to 1 plus a is 1 here. So 1 into 1 will be 2. So it will go to 2. Let's see. Let's make this as 1, right? So the point initially, which was in 1 comma 1, now moved to 2 comma 1. Okay, so this is simply how we will represent the initial configuration and the current configuration. Okay, if you draw a vector from origin 0 comma 0, small capital X, small x, and the vector which is connecting this and that, it's called displacement vector. Okay, so we can play with the motion field from here, and we can do whatever we want. This is a simple shear deformation. Similarly, we have other deformations which we will see subsequently when we move along the course. Okay, so with this I stop sharing the screen. I'll quickly summarize what we have seen in today's lecture. And if you have any question, please feel free to ask at this point in time. Yeah. So we have seen in totally the concept of force, concept of displacement, and concept of stress. So we saw force is a mathematical quantity or imaginary quantity which is used to represent displacement of body, and we saw what is displacements, how we measure displacements. We saw what is a body, by the way, the initial configuration or reference configuration of the body, the final configuration or the current configuration of the body, and how it is moving from the initial to final, and we represent that using a displacement field. The function which is actually used to relate this initial and final configuration, the reference and current configuration, we call as motion field, right, or deformation field, without time, right? And then we saw two forms, the spatial form and the material form. If we write everything in reference configuration, that is capital X, capital Y, capital Z, that is material representation. If you write everything in small x, small y, small z, that is a spatial representation we saw. Okay, then we saw two variety of problems. Number one, given the display deformation field, how to find the displacement field. It's very direct, straightforward. Number two, given the displacement field, how to find the deformation. This is a kind of inverse problem. Answer is given, we have to find the question. Okay, and finally, we have moved to stress. Here, if you are new to tensor, it will be little difficult to understand in the first glance. So keep on watching the lecture again and keep on practicing and try driving yourself. I'm sure you will understand it much better. So here we saw traction is nothing but the distribution force over a cut surface. It depends on three things. Number one, the normal. Number two, the position vector. Number three is the time. Okay, so here the important property of this traction is T's of n plus T's of n star or n dash is equal to 0, where n dash is the opposite normal, plane with opposite normal. And we saw a linear function which maps a traction, every normal vector there will be a traction vector. We saw there is a need of a linear function which maps a traction vector with the normal vector. That linear function we call as a stress tensor, second order tensor. We saw how to find the components of a second order tensor. Aij is nothing but a tensor, like how we say in vector ai equal to a vector dot with ei vector. Here we saw a ei dotted with ej is the ij component of the second order tensor. And we saw what is tensor product means. Tensor product of one vector into and tensor product of another vector is nothing but the multiplication, one vector times the transpose of the other vector. And we saw the stress components, the meaning of 9 components, right? And then we saw how to find the traction vector using Cauchy's theorem components, right? So with this I'll stop. If you have any questions, I'm happy to address. Any questions?
No, thanks.
Thank you. Sri Keshwa sir, any questions?
No, sir. No, sir.
Okay. Okay then. I'll stop recording.